Well, in part two of this lecture, we will continue on in our discussion of acid-base properties of salt solutions. Specifically, we want to first bring up that in the previous slides, the sodium ion was a spectator ion and was considered neutral in aqueous solution. It turns out, however, that many metal cations do show acidic properties in aqueous solution. Here's a picture of an experiment done that has, of course, 4 identical beakers and a different solution in each, but all the solutions are the same concentration, 1 molar. So the first solution has a 1 molar solution of, first beaker is a 1 molar solution of sodium nitrate. The second one, a 1 molar solution of calcium nitrate. The third, a 1 molar solution of zinc nitrate. And the fourth, a 1 molar solution of aluminum nitrate. And the nice colors here are not all produced by the same acid-base indicator. So in the first beaker here on the left, bromethymol blue gives us this nice green color indicative of a pH of 7, which is expected because sodium ion is neutral and nitrate is the anion, the conjugate base of the strong acid, nitric acid, so we'd expect it to be neutral. In any event, the calcium nitrate solution color comes from also from bromethymol blue. pH here is barely acidic. This beaker here with zinc nitrate shows a pH of 5.5 with methyl red indicator, and this beaker with methyl orange shows a pH of 3.5 for a solution of aluminum nitrate. Now again, recall that nitrate is a conjugate base of the strong acid nitric acid, so it would be neutral in solution. So the pH of each solution here is determined solely by the type of metal cation present. So the sodium ion appears to be neutral, which is what we said it was in previous slides. The calcium ion, a little higher charge, barely acidic. Zinc, also a +2 ion, is noticeably acidic. Aluminum, which is a 3+ ion, is really pretty acidic in water. Well, what's going on with these 3 solutions that do show metal ions that produce acidic solutions and actually increasing acidities? So let's attempt to write an equation for the formation of hydronium ion from the interaction of aluminum 3+ with water. Well, why are we doing this? Well, aluminum 3+ in water seems to produce an acidic solution, so it must be producing hydronium ions. So let's just try to write an equation. Aluminum 3+ ion plus water giving us, well, we have a little problem. This whole thing is kind of silly because obviously aluminum 3+ is not capable of being a hydrogen ion donor to water to form a hydronium ion. So there must be another mechanism in place to generate hydronium ion from the interaction of aluminum 3+ ion in water. So let's try to look at that on the next slide. In water solutions, aluminum 3+ ion is really what's called a complex involving 6 water molecules, each water molecule attached to the central aluminum ion by 1 coordinate-covalent bond. Now a coordinate-covalent bond is a single covalent bond. It's a regular covalent bond, shared electron pair, but here both of the electrons in the bond, in the quote shared pair, are donated by only one of the actors here, in this case the oxygen atom in water. So aluminum 3+ aqueous can more accurately be depicted as aluminum surrounded by 6 water molecules with the whole complex having a 3+ charge. The interesting thing about the way this formula is written is that it implies the hydrogens are attached to the aluminum. They are not. The oxygen atoms are attached to the aluminum ion. We'll see this in the following diagram where I'm going to draw one of the aluminum 3+ water connections in more detail. So right here we have a water molecule. We have a lone pair. The other lone pair has been donated to the aluminum to form what we call the coordinate-covalent bond. It's a regular covalent bond, but again, the quote now shared pair was donated just by oxygen. Well, here, aluminum ion is pretty highly charged. That's pretty highly charged for a metal ion. It's also rather small. Because of that, it has a large electrostatic pull on the shared pair of electrons here, right here. And not only that, it not only pulls that shared pair toward itself, but it has such a big influence that it pulls the oxygen-hydrogen shared pair back toward the oxygen. And what that does is it makes it easy for H to leave as H+, because if it does, H+ leaves behind an electron pair and a negative charge there, and we have H+ now free in solution to act as an acid. So this is our proposed mechanism for how a highly charged, small and highly charged cation can be acidic in solution. It undergoes this interaction with water to produce a hydrogen ion in solution. We can show a complete 3D rendition of this process along with a balanced equation like this. So here's a nice static, meaning non-moving molecular model. We've got water molecules, 6 of them, attached to the central aluminum ion by through the oxygen of the water, and we have a water molecule now approaching. And what can happen is that, of course, since a hydrogen ion is fairly easy, it's fairly easy for one to leave, it can be donated to the water molecule. We could say a water molecule is abstracting this H+ that's fairly easy to abstract. We form, and this is an equilibrium situation, an aluminum complex where there's now only 5 waters and hydroxide now attached to the aluminum. Since a hydroxide has a -1 charge, the overall charge of this is now down to +2 from +3, and we've produced a hydronium ion in solution. Now, metal ions with larger charges, in this case 3+ is pretty large, and smaller sizes, if you looked up a chart of ionic radii, you'd find that, relatively speaking, aluminum 3+ is a rather small entity. In other words, larger charge to radius ratios are most able to use this polarizing effect on the metal-oxygen bonds to produce hydronium ions in aqueous solution. Now, we won't go into great detail here comparing all different metal ions, but let's just compare sodium ion, which we've said is neutral in water, and aluminum 3+ ion, which we said is acidic in water. You'll notice aluminum 3+ has 3 times the charge of the sodium ion, and it's only about half the size. So because of this, sodium ion is neutral, and relatively speaking, aluminum 3+ is acidic because of its high charge and small size. Now, since a salt, remember, is an ionic compound comprised of both cations and anions, we must first consider the combined effects of both the cation and anion to predict whether or not a salt in general will be acidic, neutral, or basic when dissolved in water. You recall from part 1 of this lecture when we were looking at, for example, conjugate bases like acetate, we made sure the metal ion associated with that was neutral, sodium ion. When we looked at conjugate acids, like ammonium ion, we made sure it was paired with an anion that was neutral, chloride. But if you have an ionic compound with a cation and anion, if you want to predict whether that would be basic, neutral, or acidic in water, you need to look at both ions to see what's going on. Remember, you'll have this information during quizzes and exams, so no memorization is required, but it is a good idea to try to catch on to the general concepts here. So if we have a cation and an anion, or some cations and anions in an ionic compound, we dissolve it in water, we ask, what do we predict the pH would be? Well, suppose we had a compound with a cation that does not react with water. In other words, sodium ion, but other group 1A ions are neutral in water, like potassium, and also a couple of the larger members of the group 2A, strontium and barium. If we pair this with an anion that also does not react with water, like the conjugate base of a strong acid such as chloride, nitrate, or bromide, or perchlorate, you're going to get an ionic compound that's going to be neutral in water. And I have a couple of examples here: sodium chloride, potassium bromide. How about if you had an ionic compound where, again, the cation does not react with water, but the anion does? So, for example, if you had an anion, which was the conjugate base of a weak acid like acetate, fluoride, sulfite, hypochlorite, then that salt is going to be basic because the cation will have nothing to say about the pH and the anion will determine that the pH is basic. Couple of examples: sodium acetate, potassium hypochlorite. In both of these, the metal ions are neutral. They're both in group 1A, but both anions are conjugate bases of weak acids, so they'll form a base in solution. Well, how about if we had a cation that does react with water to produce hydronium ions? We talked about the ammonium ion before, but in part 2 we introduced the fact that metal ions could undergo reaction with water to form acidic solutions. Aluminum was one example. Also, if you recall, calcium, barium, or I should say beryllium 2+. What you're basically looking for is a +2 or +3 ion that's small. And you pair that in a compound with an anion that does not react with water, like chloride, bromide, nitrate, or perchlorate, you of course would get an acidic solution because it's the cation that's running the show. Examples here would be aluminum chloride, where the aluminum ion forms an acidic solution and chloride is neutral, or ammonium bromide, where the bromide ion is neutral and the ammonium ion is acidic in water. Which leads us to the final combination, which is the interesting one, or I should say the most interesting one, is what happens if you have a cation that reacts with water to produce a hydronium ion, and you pair it with an anion that reacts with water to produce hydroxide. How would you know whether to predict that this would be acidic or basic? Well, that would depend on the identities of the cation and anion. Well, let's look at an example problem here. And what I'm asking here is, would aqueous solutions of the following salts be predicted to be acidic, neutral, or basic? Well, this is potassium perchlorate, this is iron 3 bromide, this is strontium hypochlorite, and this is aluminum acetate. Well, potassium perchlorate would dissolve and break up into potassium ions and perchlorate ions. Potassium ions are neutral in solution. It's a singly charged group 1 ion. Again, you could refer to the table of examples on the previous slide. Perchlorate is neutral because it's a conjugate base of the strong acid perchloric acid. So we would expect a solution of potassium perchlorate to be neutral. How about iron 3 bromide? Well, iron 3 bromide would break up into iron 3 plus ion and bromide ion. Iron 3 plus ion, we just learned, is a highly charged and small cation and would be acidic in solution. Bromide is neutral because it's a conjugate base of the strong acid HBr, so we'd expect iron 3 bromide to act or to be acidic when dissolved in water. How about strontium hypochlorite? We said on the previous slide that strontium was an example of a ion that's relatively neutral because even though it's higher charged, it's quite large. Hypochlorite is basic in solution because it's a conjugate base of the weak acid, hypochlorous acid. So we'd expect strontium hypochlorite to be basic in solution. And finally, aluminum acetate is an interesting case because we have the aluminum ion, which is highly charged and small. We'd expect it to be acidic in solution, in aqueous solution. Acetate, you know, is the conjugate base of the weak acid, acetic acid, and is expected to be basic in solution. So the expected pH here would depend on which ion had the larger influence. One way you might go about doing this is to compare the K values. You might ask, okay, where would you find Ka values for the acidic behavior of aluminum? There actually was a table in the textbook that contains some of this information. There are other sources of this. The Ka of aluminum ion in water is 1.4 times 10 to the minus 5. The Kb of acetate, of course, is 5.6 times 10 to the minus 10. So you look at that and you say, well, the Ka of the aluminum ion is a lot bigger than the Kb of the acetate. So one might expect the solution to be acidic, despite the fact that there are 3 acetates for every 1 aluminum. And so you might ask, well, what's the answer? And I say, well, instead of doing any math, you might decide to find out the answer by actually going in the lab and dissolving some aluminum acetate in water and adding an acid-base indicator. In other words, some real science. So in conclusion here, just keep in mind that we've now opened the door to some more extensive acid-base chemistry. Compounds that don't have the word acid or base associated with them necessarily can show acidic or basic properties in aqueous solution, which makes our chemical world that much more complex and that much more interesting.